Yeah, talk about some common themes and emerging ideas from the IGS Symposium on ocean-glacier interactions this past July. To start, a little bit about me. I think I know most of you here, but I just finished my PhD at MIT and Hui in physical oceanography, working with Stiana Cherneo on various aspects of fjord dynamics, focused on southeast Greenland, and working with observations, theory, and modeling, look at various drivers of fjord circulation and heat transport. Now I'm a postdoc at Oregon State, primarily actually working with Jonathan Nash and Emily Schroyer, but also collaborating with Dave Soyland. And so to start, just a little bit about the basics of this meeting. It was in July in La Jolla, California at Scripps, and it was organized by the International Glaciology Society and chaired by Helen Fricker at Scripps, and sponsored by a variety of organizations, including FRIS, GRISO, Scripps, NASA, and NSF. As the conference name suggests, the main goal was to assess the state of our knowledge of ocean-ice interactions and processes at the ocean-ice interface and discuss what is needed for developing reliable quantitative models of ice sheet evolution. I should note this is from the conference advertisement. And the bigger goal is to understand the evolution of ice sheets in a changing climate and work towards improving predictions of global ocean circulation and sea level rise. And this involved oceanographers, glaciologists, observationalists, modelers, theoreticians, and probably other types of scientists that I'm leaving out. And I want to note this is a follow-on to a meeting 5 years ago that IGS ran on the exact same theme, and I'll come back to that in a second. So we gathered in sunny La Jolla, and we're lucky to have all our coffee breaks and lunches out on this beautiful lawn by the water. But we also did spend a lot of time inside also in talks and posters. And some basic details about the meeting. It was 5 days with 146 presenters from countries around the world. In addition to the typical poster sessions and talk sessions, there were also 2 Ignite sessions with 12 presentations, and these Ignite sessions were meant to give early career scientists a chance to talk about their perspective on the future of ocean-ice interaction research. So these were beyond sort of typical science talks, but giving early career scientists a voice to look a little bit bigger picture, or talk about where they think the field is going. And these talks ranged from how to fund science in the future, how to use robots and autonomous platforms in the future, how to work towards fully synchronous coupled models of ocean-ice interactions. And I thought it was a really cool way to get some bigger picture perspectives from early career scientists. There were a whole bunch of sessions. I'm not going to go through all these, but they were covering ocean ice topics in Antarctica and in Greenland. But I just put this up here to point out that I'm just going to focus on the sessions that focused on fjord glacier systems, mostly relevant to Greenland. And these sessions involved modeling studies, observational studies, both in Greenland and in Alaska, looking at a variety of processes like plumes, runoff, calving, and then there was a big focus on icebergs, melange, and sea ice, which I'll come back to. And so for these sessions, the science is focused on systems shown schematically here, with tidewater glaciers that don't have floating ice shelves. So I'm just going to be focused on these kinds of systems today, and where the big picture questions are about what controls the exchange of heat and fresh water between the glacier and the ocean, how those exchanges between the ocean and glacier affect the glacier and also the ocean. And when I was going through all the talks and presentations and trying to put them in categories, I found that really labels for this schematic were also good subcategories for all the different talks. So there was work presented on open ocean circulation, fjord scale circulation, then a lot zooming in on what's happening right at the ocean-glacier interface in these fjords, involving plumes and submarine melting. A lot of focus on melange and icebergs, calving, runoff for glacial hydrology, and how a lot of those things affect glacier dynamics. And today I'm just going to focus, and so I wanted to mention that a lot of the talks could be put into one of these categories, but really I was struck by how much of the work is really at the interface between these things and how these different processes are linked. So how plumes affect fjord scale circulation, or how plumes affect submarine melting, or how submarine melting affects calving, or how calving affects the iceberg and melange, and lots of studies looking at the links between these different pieces shown kind of schematically here. And yeah, for the next few minutes, I'll focus kind of on the processes highlighted in red that I think are getting a lot of the attention, at least at this meeting, which are kind of the connections between plumes and submarine melting, calving, and then icebergs and melange right near the glacier terminus. But I just want to point out that I'm definitely skipping over a lot of the subjects that were presented here. This is kind of a laundry list of the topics that were presented with some subtopics and tools. And I won't go through all these details, but there's a huge breadth of work being done on these subjects that was presented at the meeting and also beyond on all these subtopics related to glacier fjord systems. And I'm really just highlighting a few pieces of work that I think kind of show interesting samples of where the field is going and recent progress. So before I get into showing a few examples of work presented at IGS, I just thought I'd mention kind of what I saw when I compared the program from 2016 with the same conference program 5 years before. So one thing that really stuck out was there's a lot more focus on melange and icebergs and calving at this IGS meeting. Seems to be a lot of focus in the science community now on the melange and icebergs that really wasn't there 5 years ago. I also noticed that the previous meeting had much more large-scale ocean circulation work being presented, how heat is delivered to kind of glaciated coastlines on a larger scale, whereas this recent meeting was more focused in on the processes right at the ocean-ice interface. And so kind of in a similar vein, this recent IGS meeting kind of had more work that really seemed integrated and interdisciplinary, whereas the previous one was a little bit more oceanographers doing oceanography and glaciologists doing glaciology. So I think in becoming more interdisciplinary and integrated, we're definitely making progress in this field. But I do also want to point out that we still do need that bigger picture oceanography and also, glaciology and ice sheet dynamics. So this meeting, I think, really was zoomed in right at the interface and kind of smaller scale processes, but ultimately to move the field forward, we kind of need all those scales involved. So as I mentioned, there's a growing focus on the role of the melange, and at this conference there were a whole variety of studies looking at the melange and how it might affect calving and glacier dynamics. And I should note, feel free to jump in with questions. Can you guys all still hear me? I guess I should just do a quick audio check.
Yes, we can hear you.
Okay, great. So one example of recent work on trying to understand the melange is work by Alex Roble, who's a postdoc at Caltech and University of Chicago. He's trying to address questions of, how does the melange consisting of icebergs and sea ice affect the glacier, and how much force does the melange exert on the terminus, and how does that affect calving, and then also how calving events affects the melange. And so he uses kind of a novel model with a discrete element model to simulate the melange as a granulate material. And so it differs from sort of conventional ice sheet models in that there's no computational grid, but just each iceberg is individually tracked as it moves around the fjord, and then their icebergs are bound together in a matrix of sea ice. And his main results are that when the sea ice within the melange is thick, it really can suppress calving. And then when the sea ice thins, calving may resume and occur at a fast rate, and that actually a single calving event can cause widespread fracture of sea ice in the melange, which can lead to a rapid transition from kind of a terminus that's not calving to vigorous calving and mass loss. Also thinking about the melange, there's a lot of work looking at the role of icebergs and how they're melting into fjords, and the contribution of this meltwater to fjord circulation, and overall thinking about the budgets of freshwater coming from melting of the glacier terminus versus melting of icebergs versus subglacial discharge. So we have all these freshwater sources coming into the fjords, and for the most part, recent work has kind of focused on the sources of freshwater that are coming in right at the glacier from subglacial discharge or from melting of the terminus. But a lot of recent work, like what I'll sample right here, is showing that the icebergs melting within the fjords is actually an important part of these freshwater budgets. So Ellen Enderlin presented some work. Ellen is a scientist at the University of Maine, and she's showing that the meltwater fluxes actually dominate the fjord freshwater budgets in Jakobshavn and Thermalik fjords. So her approach is to use digital elevation models of the melange and differencing them between different times to look at the kind of integrated iceberg melt in these fjords that have large melanges. And she can quantify the total meltwater flux from these icebergs. Shown here is the total meltwater flux from the melange as a function of melange extent for both Thermalik fjord and Ilulissat fjord, with Thermalik fjord being the squares and the diamonds being Ilulissat. And she's finding freshwater fluxes that are really a significant portion of the total freshwater flux that is entering the fjords. And so these iceberg meltwater fluxes really need to be taken into consideration when thinking about the freshwater forcing in these fjords and how ultimately, the freshwater from the ice sheet and glaciers is distributed in the ocean. And looking a little bit closer to the glacier, or actually at the glacier, there are a variety of studies that look at terminus advance and retreat and frontal ablation. And I'm going to point out how frontal ablation might be connected to plumes that come out at the base of the glacier. And so one sample of work in this subfield is by Mason Freed, who's at the University of Texas at Austin. And he's using a whole variety of types of measurements, a lot from satellites, and looking at many different fjord systems, but I'm just going to show one particular fjord, or glacier fjord system, KS, which is in West Greenland. And through his previous work, used multi-beam imaging of the glacier front to show that there are these in-cut channels in the glacier front that seem to correspond to where subglacial discharge comes into the fjord and where plumes emerge from the base of the glacier with these in-cut channels about 45 degrees back into the glacier front. And in his recent work that he presented at IGS, it's kind of taking it one step further, looking from above now and tracking the advance and retreat of the terminus position and how that relates to plumes. So shown here on the left was looking from above, and the gray thin lines are the terminus position at various points over, I think, about 3 years. And then the pink shaded areas are where there are surface plume signatures at this same KS glacier. And what he finds is that if you look to the terminus where there typically isn't a plume, like say box 3 or box 1, which are then on the right plotted on the top and bottom, there's now time series of the terminus position. There's very little variability in the terminus. It's not really advancing or retreating all that much. Whereas if you look at box 2, the part of the terminus where the plume is emerging, he finds that there's a rapid retreat of the terminus when there are active plumes, so during the summer, and then a more slow advance during the winter. And so he's finding that the terminal advance retreat closely follows the presence of these plumes, and that which suggests that plumes causing submarine melting and potentially also causing calving is playing an important role in frontal ablation and the advance and retreat of certain parts of the glacier. So this is kind of some observational evidence that's pointing towards the importance of plumes in terminus dynamics. And the next thing I want to highlight is how plumes and submarine melting might impact calving, which is also being studied from a whole variety of different approaches. The one I'm going to highlight here is a pretty idealized one. This is work by Donald Slater from the University of Edinburgh. And so the question is, how do plumes and submarine melting affect the calving front shape and thereby potentially impact how the glacier calves? So how can you get, like what Mason saw when you have plumes of the terminus driving terminus retreat, are the plumes driving submarine melting, and then also driving calving, and how can we connect these pieces? So Donald is using a pretty idealized model of plumes at the ocean ice interface using plume theory, but for the first time he's allowing an evolving ice boundary. And so this is going to be a little schematic with ice on the left and the ocean on the right. And he imposes some plume at the base of the glacier and lets it evolve in time. And what he finds is that through the patterns of melting from the plume, you get a strongly undercut glacier terminus as the glacier advances or flows with an overhang that likely would promote calving. And also it's consistent with what we're seeing in observations like Mason's work, that there are these undercut channels in the glacier. So he shows evidence of the role that plumes and submarine melting can play in promoting calving, but he also has some interesting results about how the evolving shape of these cavities actually doesn't really feed back that much on the plume dynamics. If you plot on the right now, he has the melt rate, the function of height above the grounding line, and the melt rate profile actually doesn't change visibly as this cavity evolves and you're melting out this undercut in the glacier. And then zooming out kind of away from the glacier, thinking about how fjord scale circulation can transport heat and meltwater. I think studies are kind of looking both to how plumes from the glacier can drive fjord scale circulation, and also how the shelf ocean can drive fjord scale circulation. So kind of looking at both ends of the fjord and its role in. Is that a question?
No, I had some problems with the audio. Can everybody, hopefully everybody can still hear. Bill, can you still hear Becca?
I can.
Okay, great. So thank you. Sorry about that. It went out on my end, so I had to reconnect. Sorry, Becca.
Okay, no worries. So yeah, on the fjord scale side of things, one example of this type of work is by Dustin Carroll at the University of Oregon. And so he's looking at how discharge, subglacial discharge from glaciers can drive fjord circulation and the role of the sill in fjords. And so here are two snapshots of some model simulations that he's doing with MIT GCM. On the left is a fjord with a relatively shallow glacier, so the discharge is coming in kind of closer to the surface of the fjord. And what he finds is that the glacier-driven circulation in the fjord kind of can't bring in deep shelf waters into the fjord. The sill is pretty effective at blocking waters outside the fjord, below the sill, from coming into the fjord. But when he looks at the same fjord, but with a much deeper glacier where the discharge comes in much deeper, the fjord scale circulation actually now can draw in deep shelf waters over the sill. And this is important for thinking about how warm deep waters outside these fjords may or may not be able to get into the fjords for various fjord geometries. This is looking at kind of the fjord scale circulation that's driven by freshwater forcing. I've looked a little bit at some fjord scale circulation with more focus on how external drivers of circulation can drive exchange and transport. This has been using moored observations from Symposium Fjord in southeast Greenland, where we find a ton of synoptic scale variability, and we can attribute it to variability in a density field outside the fjord, so what we call shelf forcing. And I've explored this with numerical simulations of a fjord and shelf with a variety of forcings, but one example is with using alongshore winds in the shelf and showing that alongshore shelf winds can actually drive large volume fluxes in and out of the fjord that match up well with what we see in our observations. So that's kind of a sampling of a few of the directions I think we see that we saw at the IGS meeting, but it's definitely not a comprehensive list by any means. I just want to spend a few minutes now talking about some future directions and open questions, some things, looking through the list of talks and thinking about what was presented and what wasn't presented at this meeting about where the field might be headed. So just some thoughts about areas for progress, and this definitely has an oceanographic bias. The first, now that work by Ellen and others is showing how important the freshwater flux from icebergs is, the next step is definitely thinking about its impact on fjord circulation, both in terms of that freshwater forcing, but also just in terms of the presence of these large solid blocks floating in the fjord, and how that might impact the dynamics of the fjord and how heat and freshwater are transported through the fjord. And then also questions about how to put these icebergs into larger scale models. And people are definitely starting to work on that part of the question. But I think there's lots of progress to be made there to ultimately get the right impact of these icebergs both locally in the fjord and in the larger scale ocean. One question I think some people are starting to address, but still has a ton of open questions, is what actually controls which shelf waters get into the fjord? In the kind of coastal and estuarine world, there's been a lot of work on trying to understand where freshwater from estuaries and fjords spreads into the ocean, thinking about plumes and coastal currents, and where does the freshwater go when it leaves a fjord or estuary. But there's actually very little work about thinking about which of the shelf waters are actually drawn into a fjord or estuary. And this has been recently kind of called the estuarine inflow problem by Parker McCready at UW. I think it's a totally key question for understanding ocean glacier interactions is which shelf water masses actually get into the fjord. When we look around southeast Greenland, outside of Thermwick Fjord, we see this warm Atlantic water that's some of it's 4 degrees, some of it's 8 degrees, some of it's 2 degrees, but the water that gets into the fjord is actually in a pretty narrow temperature band, around 3 to 5 degrees, and we don't ever see any of this kind of 8-degree Atlantic water getting in the fjord, even though it is outside the fjord mouth in relatively close proximity. So really understanding the fjord shelf exchange and which shelf water masses get drawn into the fjord by a variety of drivers of circulation seems like an important next step. Also looking at the larger scale circulation, as I mentioned, this meeting was a little light on that larger scale ocean circulation, but there are obviously important questions about how freshwater forcing from the ice sheet affects larger scale ocean, and also thinking about these kind of larger scale pathways of how warm waters get to the mouths of fjords. Another thing, a lot of focus on the submarine melting, but in the end it's really observationally unconstrained, and so working on methods to constrain those submarine melt rates and partition calving and melting seems like an important step forward. And then I'm going to focus a little bit on this last point with some slides coming up and talk about some of my current work on this last point, which is really trying to understand the plumes of the glacier front and how they affect submarine melting and understanding the processes at the ocean ice boundary layer. So I'm going to focus on this for a second because it's my current focus, but obviously it's just one piece of many pieces that need to be made to make progress in this field. So when we think about what's happening right near the ocean-glacier interface, most of the progress on or the recent work to address questions right at the ocean-glacier interface is being done with models of glacial plumes. So for the most part, the observations that we have in these fjords are kind of more on the fjord scale, and they're from shipboard surveys and moorings, and that the plume dynamics right at the glacier-ocean interface is being studied with models where you have a plume emerging from the base of the glacier that's entraining ambient ocean water and driving submarine melting. And the submarine melting is going to be really sensitive to the dynamics of this plume, how fast the plume is moving and how much it's entraining ambient ocean water. So the temperature that's actually the plume is going to strongly be a function of the turbulent mixing and entrainment right near the glacier front. So plumes and turbulent entrainment are going to control submarine melting, but we have almost no direct observations, and we're using pretty unvalidated parameterizations in a variety of models. So there are kind of a couple of different approaches to modeling the near glacier circulation that are common right now. One is to use plume theory. So this is based on a wide body of research on geophysical fluid dynamics and thinking about how buoyant sources drive plumes, and it's being applied to these ocean glacier settings, but is largely untested. And it's being used then with numerical models like the MIT GCM in a variety of different ways. One kind of common approach is to tune the mixing that's being parameterized in these models to plume theory. So you're effectively tuning the mixing in the near glacier region so that the circulation matches plume theory. But it means you're also then imposing this parameterized mixing throughout the rest of the domain that may or may not be appropriate away from the glacier. And then also another approach is to kind of more directly couple plume theory with a numerical model, where you force the numerical model with some sort of plume that's with whose properties and volume flux and entrainment is dictated by plume theory. So almost all these approaches rely on plume theory, kind of assume that it must be correct for understanding what these plumes look like coming out of the glacier and how they entrain ambient ocean water masses, because none of these numerical models are actually turbulence resolving. And they also rely on some unvalidated transfer coefficients for what's actually happening right at the boundary layer where melting occurs. So some of my current work is trying to test plume theory with some new near glacier observations. I should also mention that we're not the only group doing this. Ken recently published a really interesting paper using kind of a similar autonomous vehicle with similar goals of exploring near glacier plumes and how they compare to plume theory. So I think this is kind of a new focus is trying to use these autonomous platforms to get measurements right up near the ocean glacier interface, so we can start actually testing some of these theories that are so prevalent in the models. So I've been working with some near glacier surveys from KS Fjord in West Greenland. This is with Jonathan Nash, Emily Schroyer, Dave Sutherland, and a variety of other collaborators. And we have repeat sections from the ship about 1.5 kilometers from the glacier, as well as surveying done by one of Jonathan Nash's autonomous vehicles. This one is called Rob, but basically it collects velocity and water property measurements, and it was driven around within 100 meters of the glacier, roughly, or maybe 200 meters of the glacier, in between where we were able to get shipboard measurements and the glacier terminus. And these observations give us a nice snapshot into the plume structure and dynamics. This is a cross-section of the outflowing plume with velocity on the left and temperature on the right, and you can see this core of outflowing water centered at about 30 meters depth. And we have a bunch of repeat sections that show the plume's evolution over a tidal cycle, so we can see this, the variability in its structure and dynamics. And ultimately, I'm trying to compare these observations with plume theory, so trying to test some of the parameterizations that are being used in models. And without getting into the details, what I'm finding is that the observations really can't match point source plume theory, which is kind of the common theory that a lot of models are converging on, where the basic idea is that you have a buoyancy source coming out of a point, which seems appropriate because we're finding that a lot of this subglacial discharge likely comes out of very distinct channels, in-cut channels in the glacier. And so many studies are using kind of point source plume theory, where you have a plume that forms kind of this cone coming out of the glacier's base. But what we find is that our observations really can't be reconciled with this point source plume theory, and instead the observations show that there has to be a lot more entrainment at depth. The observations actually are consistent with kind of a different version of plume theory. It's called line plume theory, where you assume that the freshwater is more coming out in a sheet or a thin line along the base of the glacier. And if we kind of assume some discrete length of a line plume, about 200 meters, we find that we can match our observations to line plume theory. And it suggests that there's much more entrainment at depth than a lot of the common parameterizations are using. And that means you have more warm water being entrained in the plumes and higher melt rates than the common parameterizations would suggest. And going forward, we're trying to take this a step further, actually, with observations from a different site. I'm working with a whole bunch of scientists, glaciologists, and oceanographers on this project at LeConte Glacier in Alaska. There's actually going to be, I think, a webinar about this in January, so I'm not going to really talk much about the bigger project, but just mention that it has a whole variety of oceanographic glaciology components, looking at LeConte Glacier in southeast Alaska. But the little part that I'm focused on is, again, the near glacier dynamics and trying to really understand these turbulent fluxes and plume-driven circulation right at the ocean-glacier interface. And so this past August, we did a bunch of surveying, both by ship and with an autonomous vehicle, similar to the one used in West Greenland, where we were able to get right up near the glacier terminus, measure velocity and water properties. And also we did a ton of turbulence profiling, where we're actually trying to directly measure the mixing and turbulence, that important entrainment component of what's going on near the glacier. And we're finding some very high dissipation rates right in the outflowing plume near the glacier. And yeah, ultimately, the goal is to combine these near glacier observations with some LES modeling. This is a sample run done by Eric Steelingstad. So this is a turbulence resolving model. And so the idea is to combine our near glacier observations, including turbulence measurements, with this turbulence resolving model to really get at the dynamics and entrainment in these plumes, and ultimately try to understand the controls on submarine melting. And then I just want to end by kind of stepping back and looking even bigger picture about how we can move this field forward, and just some thoughts on future directions. The first is point out the importance of looking at sites both in Greenland and outside of Greenland to both understand a variety of glacier fjord systems, but also kind of take advantage of certain sites where more comprehensive measurements can maybe be obtained, like LeConte Glacier. And I think there'll be much more discussion about this particular project in January. I think an important goal is trying to have some more direct comparisons and testings of observations with models and theory, really trying to bring those two components together. And this definitely requires getting more observations. There's a lot of modeling that's being done that we just don't have the observations to test. So collecting more observations, but also in kind of a hypothesis-driven way. The other thing I wanted to point out is that I think the field can probably make rapid progress by building on the existing understanding of estuarine and coastal dynamics. There's a huge body of work on river estuaries, and they're definitely and lower latitude fjords that don't have glaciers, and these fjords in Greenland are definitely outliers in the kind of estuarine world. But I also think that the glacier fjord community is a little bit at risk of reinventing the wheel, that there is a lot of good foundation there to build upon. I think there's a lot of crossover for understanding these glacial fjords that can come out of understanding estuaries that have been studied in depth. And that one way to promote this is increased interaction with the coastal physical oceanography community, bringing more coastal dynamicists into the Greenland ocean ice community, and really trying to build on the existing understanding of coastal dynamics. I think I'll just end there, and thanks, and take any questions.
Thanks, Rebecca. That was great. I apologize for getting your organization, your institution incorrect in the introduction. And I thank you for the advertisement for January's meeting. Does anyone on the phone have questions? Okay, I have a couple. So the first one sort of feeds into one of your last bullet points, and that was when you were talking about I guess it was maybe Dustin Carroll's modeling, and you indicated that if you had a shallow plume from the glacier, you couldn't suck in the warm, deep water from the shelf over the sill, but you could when you had a deeper glacier. What were the dynamics that drove that? It looked like there was more mixing with the deeper plume, but I wondered what actually caused that inflow to increase.
Yeah, that's a good question. I mean, I think So what we're seeing here is in the end of these plots is the velocity field, kind of on the right side of each of these things. And then in color is, I think, a tracer that he's put in a discharge in blue and outside the sill in red. And so for the shallow discharge case, I think he's primarily finding that the circulation is really contained to the the top of. Oh, sorry. Do you not still have screen share up? Is this?
Decca, I made a mistake and took it off because I thought you were taking down your presentation, so I pulled up the other one. I made your presenter. Can you show it from the one that had some errors in it?
Sure.
Is it there?
Oh, yeah. Sorry. So I just was.
Okay. Yep.
So,
yep. My bad. Sorry.
So yeah, the blue is, I think, a dye in the subglacial discharge, and the red is a dye put in the passive tracer put in the waters outside the still, and then the little panels on the right side of this plot are showing the velocity field. And so when the discharge is shallow, he's primarily getting a surface trap circulation, and so I think there's just very little circulation down at the depth of the sill, and you just see the discharge spreading at the surface and almost nothing coming in at depth. Whereas when you put the discharge at the bottom, and you have this now circulation that kind of extends the whole depth of the fjord. You can see the outflow is thicker, but also now there's this circulation at depth that's allowed to draw in that water on the other side of the sill. And yeah, I think mixing is definitely a fundamental part of this, that both mixing within the fjord, but also the fact that this discharge is mixing with deep ambient water and then upwelling is driving the circulation and allowing to draw in that deep water. But yeah, definitely Dustin would have to speak on the details of these dynamics.
Yeah. So I was just thinking back to coastal plain estuaries, and when you have a highly stratified coastal plain estuary, you have a weaker inflow at depth, but it tends to be distributed, I believe, over the entire depth of the deeper layer, whereas in a more mixed coastal plain estuary, you have the much stronger inflow. But again, it's distributed over the full lower layer of the estuarine circulation.
Uh-huh.
I just didn't fully understand the dynamics here. So the other question I had dealt more with a comparison between the Arctic and the Antarctic, and I wondered if there was any consensus about whether understanding of the circulation and the processes affecting ocean-glacier interactions were transferable between the two poles or not.
Yeah, it's a really good question. I mean, I think at the meeting, definitely, things were a little bit divided between Antarctica and Greenland, both, chronologically, Antarctica was the first couple of days and Greenland was the second couple of days. And I think there wasn't that much focus on like the Western Arctic Peninsula glaciers and fjords that are kind of more directly analogous to a lot of the systems in Greenland. So it did kind of divide into the Antarctic ice shelves and then Greenland tidewater glaciers without ice shelves or tongues for the most part. But I mean, I think there definitely are a ton of there's shared dynamics and there are differences, and I mean, I guess that's obvious, but it does seem a little bit like the two communities are working in parallel, based on at least what you see at IGS. But I think there's increased, crossover, and it seems like more people are working in both environments, which I think is a great way to, promote the exchange of ideas between these different communities. I mean, certainly the role of, I did see at least, thinking about Plume today, there definitely seems to be a lot of common discussion about plume dynamics at vertical glacial fronts where there is discharge versus at sloping ice tongues and ice shelves where there usually isn't much discharge. And I do think, at least on this particular subtopic, there is a lot of talking and communication and trying to understand that transition and what the shared dynamics are and what the differences are for the plume and submarine melting dynamics as the function of the tilt of the ice, whether it's horizontal or vertical or in between, and whether you have this extra buoyancy forcing from discharge. And I think people are really trying to explore the parameter space between the kind of extremes, between the totally vertical front and totally horizontal. And so I think, as people explore that parameter space between the extremes, it's really allowing, I think, for both Antarctic and Greenland studies to kind of benefit from each other and put their work in the context of the other, because in the end, there are a lot of common physics and dynamics.
Okay, thank you. Anybody else on the phone or on the webinar have a comment or a question?
I can jump in here. This is Erin Pettit. Can people hear me?
Go ahead, Erin.
Yeah. Yeah, I just wanted to follow on with that. I think there's actually quite a bit of overlap in terms of ideas and processes. The scales and the availability of data at that boundary are quite a bit different in Antarctica. For example, we really are limited right now in the data that we have available in the Antarctic Peninsula fjords. They're also a little more geometrically complex, it seems like, at least from the ones that I've been focusing on, that we do have a little bit of data in. But I think this is one reason that we really actually do need to work across all the systems, the Antarctic, the Greenland, and the Alaskan system, because we can learn so much from each of these different systems because they have different parameters. Like the discharge along the Antarctic Peninsula is much, much, much smaller. And so we're trying to understand, like, how much does having such limited discharge limit that circulation, or how does that end up affecting the different estuarine style circulations? And so it's really important, I think, to understand all of these places that we look to the others to get at that. So yeah, I think I've seen a lot of overlap in my work, and that's one of the reasons I keep poking my head into a lot of the different groups that are working on stuff. So that's my 2 cents on that.
Okay, thanks, Erin. Anyone else? All right, hearing none, thanks again, Becca. That was a great presentation.